Hey, let's do some example optimization problems. And here's the first one. We're going to build a can that holds 20 cubic inches of some sort of liquid. So like we're talking a soup can or a soda can, that kind of thing. And we're looking for the dimensions of the cylinder that requires the least amount of materials. So we've read the problem carefully. Now we need a picture. And our picture looks something like that. The next step is to introduce some variables. There are two interesting dimensions to a cylinder, and they are the radius of the cylinder and the height of the cylinder, which I have called R and H. Our goal is to find the dimensions of the cylinder that requires the least materials. Well, the materials of this can are all in the top and the bottom of the can and around the sides of the can, and so what we're trying to do is make that as small as possible. And that concept, the sides of the can and the top and the bottom, is called the surface area, and making it as small as possible is minimizing it, which is to say that our objective is to minimize the surface area. And here we come to what is probably the hardest part of this problem, which is coming up with an expression for the surface area. If we're going to try to minimize the surface area, we're going to need a function that describes the surface area in terms of the variables R and H. And the surface area is really made up of three parts. There's the top, the bottom, and then the sides. The top and the bottom are not hard. Those are both circles. And we know the area of a circle. The area of a circle is pi r squared. So we've got two of those, one for the top, one for the bottom. Now, imagine that you've removed the top and bottom from this can, and you've taken your tin snips and you've cut along the side of the can along that dashed green line that I've drawn in. You can then peel apart the can. You can start to open it up and open it up some more. And if you open it up all the way and flatten it out, then you see that you come up with a rectangle. And it's not hard to see that the height of the rectangle is just the height of the can or the cylinder, h. The width of the rectangle is slightly trickier, but it comes from going around the length of the top of the can, or the circumference of the circle that is the top of the can. And the circumference of a circle is 2 pi times the radius. And that gives us an expression for the area of the side of the can. It's 2 pi r times h, length times width, or height times width of the rectangle. And putting that all together, we've now come up with an expression for the surface area. It's 2 pi r squared plus 2 pi r h when you add the top, the bottom, and the sides. And all that work was just to come up with an expression for the surface area, which I've written here and I've abbreviated as S, and cleared away the work so that we have some room to do some calculations. And what are those calculations? Well, I'm looking for a minimum of this function, but unfortunately this is a function of two variables, and so now I need to try to eliminate one of those variables so that I can do some calculus. And how do you do that? You use the constraints of the problem. And in particular, the constraint of the problem is that the can is supposed to hold 20 cubic inches of liquid. To make some progress with that, we'll need an expression for the volume of a cylinder. The volume of a cylinder is pi r squared h, and I would give you that on a quiz or an exam. And so since the cylinder that we're trying to construct has a volume of 20 cubic inches, we have that 20 is pi r squared h. And now we can use that to solve for one of the variables, r or h. If we tried to solve for r, we'd end up with something that had a square root in it, and it would be a little bit more complicated than it has to be. It probably makes more sense to solve this for h. And doing so, we get that h is equal to 20 over pi r squared. We can now plug that into our formula for the surface area. And after doing a little simplifying, you get that the surface area is 2 pi r squared plus 40 over r. Now we're in great shape. We have the surface area in terms of a single variable, and so we can try to find the relative extrema of this function. And to do that, you take the derivative, set it equal to 0, and solve. Notice that right in here, where I had this r squared in the denominator to make some progress algebraically, what I did was multiply both sides by r squared to get this expression right here, 4 pi r cubed minus 40 equals 0. And then from there, it's not hard to keep on working to get to this answer right here, that r is the cubed root of 10 over pi. We should, of course, verify that our critical point is in fact a relative minimum. Probably the easiest way is the second derivative test. Take the derivative right here and take its derivative, which is easier if you rewrite the 40 over r squared as 40r to the negative 2. And then you get this expression here for the second derivative and plug any positive number into that expression. So it might look intimidating that we're trying to plug in cubed root of 10 over pi, but that's a positive number. We've got 4 pi, which is positive, plus 80 over some positive number cubed. That's a positive number. That's all you need to say that this critical point is a relative minimum. We're nearly done. We could check endpoints, but the endpoints are when r is 0 or h is 0. And if you're trying to get 20 cubic inches of liquid, if r is 0 or h is 0, the volume is 0, and so it can't possibly happen. And so really there are no endpoints to check. And all that's left is to answer the question. We're looking for the dimensions of the cylinder. Well, so far all we've found is the radius. We also need the height. And from this expression right here, we get that the height is 20 over pi times the cubed root of 10 over pi all squared, which if you like, you could rewrite in a slightly simpler form, 20 over pi times the cubed root of 100 over pi squared. And to formally answer the question, don't forget to include the units. The radius should be the cubed root of 10 over pi inches, and the height should be 20 over pi times the cubed root of 100 over pi squared inches. Just one more quick thing before we move on to the next example. Don't let the numbers intimidate you here. I mean, the work was no different. We came out with the radius equals the cubed root of 10 over pi. Same work as if we had come out with the radius is equal to 17 or 5 or 11. It's just that maybe you never met the cubed root of 10 over pi before, but now you have. It's like you made a new friend. All right, moving on to the next example. This one is a classic. Find the dimensions of the largest open box that can be constructed by cutting the squares out of the corners of a 4-foot by 6-foot sheet of cardboard. Well, what does that mean? Well, I'm glad you asked. I'm going to show you. Here we have our 4-foot by 6-foot sheet of cardboard. And if you imagine taking a pair of scissors and cutting out squares, equal squares from each of the 4 corners, then there are these flaps left over that you can fold up, and you end up with a box that has no top, an open box. Bottom, 4 sides, no top. So we've read the question carefully, and we have drawn a nice picture. The next step is to introduce some variables. And if I call the length of the side of one of these squares x, well, it's a square, so all of its sides have length x. And all 4 squares are the same size, and so they all have side length x. What's my goal? My goal is to build the largest possible box. And so what am I talking about? I'm talking about the box with the biggest volume. In other words, my objective, maximize volume. And the volume of a rectangular solid is length times width times height. We know the height, that's going to be the value x that we've already chosen. And I can label these sides L and W for length and width, and it turns out that it's not hard to compute what they are because we know that this is a 4-foot by 6-foot sheet of cardboard. For example, this whole distance from here all the way over to here is 6 feet, and we've taken off x over here and x over here, and L is what we've got left. Which is to say that L is 6 minus 2x, minus an x for each of the 2 corners. And by the same reasoning, W is 4 minus 2x. And that lets us rewrite the volume in terms of a single variable. The volume is 6 minus 2x times 4 minus 2x times x. We're going to want to do some calculus on that in order to find the relative extrema. I suppose one thing we could do is use the product rule with that product of 3 functions, but it's certainly easier if you do the algebra first, and distribute that expression and simplify it to 4x cubed minus 20x squared plus 24x. So you can go off on the side and verify that that is true. It is. We're now ready to find the critical points. And to do that, you take the derivative, set it equal to 0, and solve. And after you get it down to this point, 3x squared minus 10x plus 8 equals 0, you spend a little time trying to factor that, and you find you can't. The good news, though, is that we know how to solve every possible quadratic equation. Any equation of the form ax squared plus bx plus c equals 0 has the solution x equals the opposite of b plus and minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula, a beautiful thing. And so you apply the quadratic formula, you get it down eventually to this step right here. There's some simplifying you can do from there because the square root of 28 is the square root of 4 times 7, and the square root of 4 is 2. So that's where we got this 2 square roots of 7 right there. And then we can factor a 2 out in the numerator and cancel with the 2 in the denominator to get this as the final answer. Two solutions, x is either 5 plus the square root of 7 over 3 or 5 minus the square root of 7 over 3. And this is the first time we've had two critical points in one of these problems, and you could argue that we should test them and see which one might be a maximum, because our goal is to maximize the volume. But it turns out that only one of these critical points makes any sense. In particular, there's a largest possible size for x. Since this side here is 4 feet long, the biggest x could possibly be would be half of that distance, which is 2 feet long. Which is to say that I know that x is less than 2, and I think it's completely clear that the square root of 7 is some number bigger than 1, which means that 5 plus the square root of 7 is bigger than 5 plus 1, which is 6, which tells us that 5 plus the square root of 7 over 3 is bigger than 6 over 3, which is 2. And so that critical point is too big. There's no way that x is equal to 5 plus the square root of 7 over 3. And that leaves us with just a single critical point to consider. X equals 5 minus the square root of 7 over 3. We should check that that point is a maximum. I will once again rely on the second derivative test. And you take the second derivative and you get 24x minus 40, and then you plug in 5 minus the square root of 7 over 3 into that second derivative. And it turns out that it works out quite simply, really, and you get negative 8 square roots of 7, a negative number, and so we do have a relative maximum at this critical point. And to fully answer the question, the dimensions of the open box that we come up with are 6 minus 2 times 5 minus the square root of 7 over 3 feet, by 4 minus twice 5 minus the square root of 7 over 3 feet, by 5 minus the square root of 7 over 3 feet, after cutting out corners of size 5 minus the square root of 7 over 3 feet. And I suppose we should simplify those numbers and do a little bit of arithmetic right there, but we've done all the calculus and we'll call it good enough for now. Okay, we had a little practice doing some optimization problems. You should be all set to complete the homework now. Have some fun with it. Looking forward to seeing you in class.